Hello, welcome to my channel. I'm an A-level student, and this channel will be mainly focused on me posting math things I discover. I'm only a math student, so will also be a learning journey for me. I'm making this video because I haven't seen anybody on YouTube kind of proving this idea, but we're going to be looking at a product rule for n functions. So we're going to start with basic observation. We're going to look at regular product rule. Now I'm not going to prove this in this video, but I might make one in the future proving this. Now we'll just take that to be true. Now as we know, the derivative of the product of two functions is equal to, well, taking fg, that's equal to f prime g plus fg prime, as we know it. Now let's look at a product rule for three functions. Now what we can do is we can group the first two functions together, f and g, and we can use a regular product rule to differentiate the whole thing. Now you'll notice that we still gotta deal with the f and g all differentiated, but as we know, the regular product rule, we can substitute that in, and we can expand the brackets, and there we have it. That's our triple product rule, triple function product rule. Now we can do the same thing with four functions. So I'm now shortening it to A, B, C, D just to make it look less messy. Again, we group the first three, and we can use regular product rule, and then we substitute in our triple product rule. We can substitute that in. We expand the brackets, and there we go. That's our four function um, product rule. Now we can do the same thing for 5 and 6, which will look something like this. Now you may have noticed a pattern here. The basic idea is you basically gotta differentiate each function once, and you just keep the rest. So you end up with some. So as you know, if there's two functions, you're gonna end up with two um, products adding together in the end, and basically you just gotta differentiate each function once. So four functions, you have four products adding together, and you have the first one differentiates A, and then B, and then C, and then D, and that's our product rule. Now this is enough to demonstrate that the rule does work for really any positive integer, but you can prove it by basic induction. So we're going to start with defining capital Fn, and that's going to be the product of f1, f2, f3, all the way up to fn. Now we got to prove that the derivative of that is equal to um, f. We're going to start with f prime, f1 prime of x multiplied by capital Fn of x divided by f1 of x. The reason I'm writing it this way is because obviously n can be anything, and it's hard to. I don't know how else to write it, so you can have however many products per term depending on the n. So I've just decided, well, it's going to be every term of the whole function except the one that's being differentiated. So I'm taking the whole function, I'm dividing by the one that's being differentiated. And we do the same thing for every term up to the end. Now we've got to prove that for all positive integers n. So we'll start with n equals 1. That's quite simple, as we know that capital F of 1 is equal to f1 of x. So the numerator and denominator cancels, and we end up with this equation, which is by definition is correct. By definition is equal, so we know it's true for n equals 1. Now let's say it's true for n equals k, which will look something like this. Now we gotta try n equals k plus 1. So because of how we define the capital Fn, we know that capital Fk times little f k plus 1 is going to give us capital F k plus 1, as that's how we defined it. So we're going to split that up that way, and this f capital Fk, we know that is equal to this expression, so we're going to sub that in. Oh wait, first I use product rule to split it up. Now I sub that in, and we have this entire sum multiplied by this function here, and the last term is this. Now we can expand, you will get this messy function with a little f k plus 1 in each term, and we'll see what we can do with this. Well, as we know that capital F k times little f k plus 1 gives us capital F k plus 1, so we can sub that in, and that simplifies it, and you realize that each term is already matching up with our original expression except the last term. Now we need to notice here is that we can rearrange this equation and we'll get that capital Fk is equal to capital Fk plus 1 divided by little fk plus 1. So we can then sub that in, and now we've got every term into the format of our original expression, and we know that it works for n equals k plus 1. And because we know it works for n equals 1, and if it's true for n equals k, then it's true for n equals k plus 1, it must be true for all positive integers by mathematical induction. If you guys have any more recommendations, please leave it in the comments down below, and I'll see what I can do with it.